Good morning to everyone, and I'm really glad to be joining you for week 14 for if I'm right, week 14 for your cohort training class. I should say that I feel like AI Saturday Lagos and Women DS, we're more like sisters at this point. So when Tejimade asked me, I felt like, okay, yes, I'm happy to do that. I get to meet the rest of the community, and then we could see even in the future how we could work together. So I'm really happy to be joining you today. And without much ado, I would be teaching on unsupervised learning as already communicated. And I included just the logos of organizations that I'm part of. The Women DS, which I already mentioned, is more like a sister to AI Saturday Lagos at this point. And then also in University of Zealand with Tejimade. Also, I know that sometimes I can have the tendency to speak really fast, but I'm going to be very cautious because I used to do that when I was teaching with my students. I try to be cautious and speak as slow as possible. But if at any point in time you still think I'm speaking too fast, please just put up your hand and speak up, or you could just write in the chat, and I'm happy to slow down at any point in time. So to get started, the outline for today's courses, I know you have taken some few lectures on machine learning and machine learning types. So I just wanted us to do a recap because it's a continuation or a build up on this before we focus now on unsupervised learning. And under this, I wanted us to look at how you apply unsupervised learning and what are also the challenges with unsupervised learning. Before we now move into the focus of the lessons, which is the types of unsupervised learning. And under these types, we are looking at just two for the class. I put them as class train and dimensionality reduction approaches. Under the class train approaches, we are going to look at K-means and Gaussian mixture models. And under the dimensionality reduction, we'll focus our attention on PCA, and then we would take a feedback and then also the summary of today's class. So let's see how we go for a jolly ride. Well, for every class, it's important to know how you want to know if you picked anything from the class. So after the class, my learning outcomes are that you should be able to at least define what unsupervised learning is, and also understand how this type of machine learning differs from other types of machine learning. You should also be able to identify the applications where you think unsupervised learning would be beneficial. And focusing on the types of unsupervised learning, I would expect that you should be able to explain the key concepts behind K-means, class train, and describe Gaussian mixture model, and also understand the role of the EM algorithm. You do not have to get worried about what is EM algorithm, what is GMM, what is K-means. We would look at what these things mean in a few minutes. So just don't get nervous about anything. And then we would focus our attention on also looking at the difference between K-means and GMMs and identify cases where Gaussian mixture models would be more appropriate to use. And then finally, you should also be able to explain how PCA works as a technique. So this is literally this entire class again. I just broke it down as to how you could evaluate yourself. So if after this class, you pick each of these points, are you able to define this, you tick it, then yay, you are making progress. So this is just pretty much about what the learning outcomes are. So yes, to get started, we want to look at the recap on machine learning. So I know you have looked at this already, so I just decided that let's make this as a short quiz. So maybe I should also give a heads up that would get a bit of quizzes along the way, just to be sure that everyone is following along. So you can scan this and then type in the previous week, what did you learn machine learning meant to you? What is machine learning? From all of these responses, I want to believe that most of us at least still remember what machine learning actually meant from our classes. And most of these responses are right. And just to formalize, I think using the definition of learning in particular from the book of Joshua Benjo and Goodfellow, they define learning as a computer program that is set to learn from experience, okay, with respect to a class of task T and performance measure P. And its performance at task T is measured by P improving without experience. So it's similar to what you mentioned, that AI is learning from data, or letting computers learn how to do a task. So for example, I like using this example where it's a loan approval system. And this loan approval system is the particular task, being able to determine whether someone will pay a loan or not is the task. And your performance measure is whether you're accurately able to identify with your machine learning model that these people are actually paying back a loan or not, which is your performance measure. So if your performance at being able to tell whether someone will pay a loan or not, measured by whether you get the accurate predictions that they actually pay back, improves with several experience, then you can say you're learning, right? So this is just a formalization of most of the responses that you gave as the definition of what you understood as ML. I brought this so that we could just quickly move into reminding ourselves also on the three major types of machine learning. From the previous class that I attended, I know you had a class on supervised learning as well. And we learned from the class that supervised learning is largely learning from inputs and outputs that are provided to a model. So in the example of the loan approval, the inputs are the features that you have. So for example, the educational level of the person, the income level, the age, where the person lives, several information that you think would be enough for you to learn from to be able to tell if someone would pay back a loan or not. And so with supervised learning, we are provided the inputs and also the outputs. And we can talk about application examples ranging from predicting house prices, breast cancer, fraud detection. And then we have some example types of algorithms for supervised learning. There are several of them, but this is just to help you just recap that, yes, you looked at these things, which is linear regression, logistic regression, support vector machine, and many others that you can think about. On the other hand, we also have the reinforcement learning. And largely with reinforcement learning, what we are doing is that we are learning from letting the computer learn by itself from taking actions and getting rewards. When I explain reinforcement learning, I also try to think about it like how even we humans, we learn. We humans learn from doing certain things and learning from them. So a good example here I just learned right now was that I thought just having the QR code would make it much easier for people to scan and then just go and then give the responses. But I noticed that not everyone could immediately scan before I moved to the slide where we could see the responses. And so it's usually useful to put in the link. So the action I took was to provide this QR code, and then I got a reward, which was how you responded to whether I am able to, whether you're able to scan the code and write your responses or giving the link. So now I learned that the next time, even if I'm doing it, I do the two, I provide a QR code, and equally I provide a link. So you can think about reinforcement learning just by taking actions and getting some rewards, and then you learn from them and get better. And we can think about application context of reinforcement learning, and we can think about self-driving cars, we can think about robots learning to walk, and many others. Equally, we also have some example algorithms, which are Q-learning, model-based evaluation. I know for your cohort, you are not taking any class on reinforcement learning in particular, but in case you're interested in knowing more about reinforcement learning or how you can learn to take actions without getting reward, you probably could follow up and check on Google on this material, or I'm happy to provide some reference links to this. I know that some people would be interested in this area. I left the unsupervised learning for the last because that's the focus of our class today. And today we want to learn that, okay, we learned already that you can have inputs and outputs that you provide to the model, and we say that is supervised. On the other hand, when you only have the inputs and you don't have the labels, then you are only given the inputs and you have to draw insight from hidden patterns, then we say it's unsupervised learning. You're doing this without a teacher. So again, with a loan approval system, we just give you the data. We don't tell you which people are going to pay back the loan and who are not going to pay back the loan. So you just have the data of people's education, where they live, their income level and stuff. So with unsupervised learning, what you need to do is to be able to draw insights through some hidden patterns in the data set. So with such a data, you may find that, okay, people who actually have some educational level, like higher educational level, tend to have higher amounts of income. That's an example. And you only get to know this through unsupervised learning. Okay, and some application examples of this are customer segmentation, weather situation, pattern recognition. And we also have some example of unsupervised learning algorithms. And a few of them, the good news is that we would cover all of these examples I've mentioned in class, which is K-means, PCA, and Gaussian mixture models. Okay, so to be sure that you all follow and hopefully get the difference between supervised and unsupervised learning, I have a pop quiz here. And with this one, I think it's easy for you to just write in the chat, okay, write in the chat what you think the primary difference between supervised, unsupervised learning and supervised learning is in machine learning. So here I provided multiple choice answers. So the first is that we say you just have to choose one. We say that A is in unsupervised learning, the algorithm is provided with labeled data, while in supervised learning, the algorithm works with unlabeled data. And then B, unsupervised learning uses a model to make predictions, while unsupervised learning does not involve making predictions. And C, supervised learning requires the algorithm to find hidden patterns in the data, while unsupervised learning uses predefined patterns. And then D, in supervised learning, the algorithm learns from labeled data with known outcomes, while unsupervised learning deals with unlabeled data and seeks to discover patterns or relationship on its own. Okay, I'm seeing lots of responses as D. I hope you all do agree this is D, or it's because a lot of people are saying D. Why not A? Why not B? In D, we say that in supervised learning, the algorithm learns from labeled data with known outcomes, right? And I mean, the labeled data just means that you have the inputs and you have the outputs, which you can think about them as your targets. And okay, I should stop using the mouse. While unsupervised learning deals with unlabeled data, right? So here you just have the inputs, you don't have the outputs. And our main goal here is that we want to discover some patterns or relationship on its own just by giving this input data. So absolutely the right answer is D. So, all right. So like I said, +1 to anyone who answered D to this question. And then this moves us there. And now we know what unsupervised learning is. We are able to differentiate between unsupervised and supervised learning. We want to look at application of unsupervised learning. And the first is, again, I should say that there are several applications, but I just had to make it, just choose a few and focus on these. But there are several applications that you can think about many more. So under class train, we have market segmentation. So a good example for market segmentation you can think about is in the telecommunication industry. Most of the times they have, for example, everyone is able to register your SIM card. They're able to monitor how often you buy credits, if you buy data, a whole other information about different clients. And so with market segmentation, they are able to focus their attention on which particular kind of customers probably prefer buying data that is less than 2 euros, for example. And once they identify such customer, they're able to fine-tune packages that could suit them. Or it could be possible that some customers from some particular locations in the country prefer some particular data bundles. And they could actually focus on fine-tuning their bundle packages to really provide or target them so they can actually keep buying more data. Or they could think about other example would be that sometimes some customers used to buy data. After a while, they stop buying data. And the trend they've noticed is that when it happens that way, these customers tend to switch or churn to a different network. So when they see that the pattern of you buying data begins to drop within some particular group, then they can think about, okay, what could be the reasons why this person is no longer buying data? And then they can provide some sort of packages that would suit them, and then they can make them stay and not let them move to different networks. So you can think about market segmentation in different industries. Telecommunication, I just mentioned. You could think about banking. There are other different areas, but the idea of market segmentation is just to be able to group similar characteristics of your customers and then provide some services to suit them. The second is dimensionality reduction. And with dimensionality reduction, we focus, an example here is feature extraction. Most often, sometimes we are provided with large amount of data. And with this data, it's hard to work with. And so sometimes we want to be able to extract meaningful features from the data and use this to build whatever algorithm we want to build. So with feature extraction, unsupervised learning can help us with feature extraction and help us extract the most important or useful features. And under this dimensionality reduction, we'll see shortly that PCA can help us actually do this. And then the other application I want to touch on is movie recommendation. So I think with this example, probably most of us have experienced this with, let's say, YouTube. You go on YouTube and then you see them recommending some particular movies to you. They do this based on the previous sort of videos you have liked or watched, and then they recommend these videos to you. You could think of Netflix also doing the same thing, or even shopping. You go on Amazon or other online shopping centers, and you find them recommending certain products to you. And that is just based on all the things you have liked in the past, or things you have even bought in the past. They use this to now recommend things to you. So unsupervised learning also helps us do this. So coming back on feature extraction, so you can think about feature extraction as, okay, let me give the example of this, like working with images in particular. Most often you working with some form of or images, let's say, MNS is small, but let's say there's this data set they call Celeb A, which is pictures of just a lot of celebrities. And the idea with feature extraction is that you have this data set, and usually when you pick an image, it's just a huge matrix, right? So it's a big matrix, at 256 by 256 matrix. Like, if you're thinking about images, they are mostly just matrices, okay? So now you have this huge matrices, and let's say that in this, and they represent images of celebrities. And in this, you want to be able to identify only people by their eyes, for example, okay? And some parts of this metrics actually is where the eyes of, or that's what defines the eyes of someone, right? So with feature extraction, instead of working with the entire metrics, then you try to extract the most important features from this matrix. Then you work with that to be able to, let's say, classify or identify if someone has an eye in the cell A data set or not. I'm not sure if this is actually a very good example. Let me see if there's this. Okay, the other good example would be social media data, because that also comes in large numbers in every second. So with social media data, for example, if we pick Facebook or Twitter, for example, you can collect lots of data. So you can collect people's their browsing pattern. You can collect their retweets, how often they comment, several features, right? And with this, you provide this as an entire data set, right? And now working with this entire data set, and maybe your goal is just to be able to identify whether a tweet is a spam tweet or not, right? Or in most tweet cases, it's usually sentiment. You want to be able to identify if this was a tweet with a positive or negative sentiment. So you collect this huge information of different users' tweet patterns, and then based on this, you want to build a system that is able to identify if a tweet is spam or not, right? So with feature extraction, if you use feature extraction in here, what you want, or what you will be able to do, is to extract what particular information from this tweets of users is important to help you tell whether a tweet is has a positive or a negative sentiment. So you could notice that, okay, identifying for verbs or adjectives, and if these adjectives have negative connotations, then you could conclude, or you could say that, okay, these are tweets that have negative sentiment. But you need to be able to find a way to extract these features from this entire data set. And so just taking out the most important information from it and working with that subset is what we call feature extraction in this case. I don't know if that makes sense. So in as much as we think how useful this supervised learning technique could be, there are also challenges that can be faced with this. And some of the challenges is the lack of ground truth label. So we already understood that a main thing about unsupervised is that we do not have ground truth. And the lack of this ground truth makes it difficult for us to actually measure the accuracy, because you do not have a particular ground truth. So how do you measure that? Okay, is this the right thing you are doing? If you are recommending a movie to someone, is this the right movie you're recommending to the person? Because you actually don't have any ground truth labels of the kind of movies that this person would like, right? And sometimes when you have your results of unsupervised learning, it could be very difficult to even understand, especially when you do class train. You can do a class train algorithm, and then you find it hard to understand, okay, what do these 3 clusters or 4 clusters even mean? So that's another challenge of unsupervised learning, and it could also take you some time to interpret the results of an unsupervised learning technique. So these are a few challenges of unsupervised learning in particular that I just wanted to mention in that regard. If that is okay, I think the next thing we want to focus our attention now is, okay, we already looked somewhat at this, the type of unsupervised learning, but just to make this much clearer, we have the unsupervised learning, and we have it can be divided into 3 different types or techniques. So the first is clustering, the second is dimensionality reduction, and the third is association. But the focus of our class today would be on only clustering and dimensionality reduction. I will just continue. So just a recap, we looked at what supervised and unsupervised learning was, and we looked at the application of unsupervised learning, and we then focused our attention on the challenges of unsupervised learning, and we said the 3 techniques for unsupervised learning are clustering, then dimensionality reduction and association, but we are focusing on clustering and dimensionality reduction. So the first part that I want us to focus on is on clustering. And under clustering, we would look at two different algorithms, which is K-means and then Gaussian mixture models. But first, we're going to start with K-means. So first, K-means is basically a type of clustering algorithm that is easy to visualize, giving some collection of data points. We want to, so if you have a collection of data points, we want to be able to find some K centers or centroids, such that for each data point, from each data point to each of the cluster that it belongs to, the distance is as small as possible. So for example, with this image here, we are given this data sets, and our idea is that what we want to do is to find K different centers. So you can have different centers. And then, so for this, you have a center here, you have another center and another center here. Our idea is that for each data point around this particular center, we want the distance from this data point to that center to be as small as possible in this cluster. And if we pick this other cluster and we have the center here, our goal is that we want the distance between this data point and this center here should be as small as possible. And of course, the distance from this data point in this cluster. Yeah, so I was saying if we have a center here and we have another center here and another center there, the distance from this data point and this should be as small as possible. The distance from this center here and this data point to be as small as possible. However, the distance from this data point to this center should be as large as possible so that you can know that this is one cluster, this is another, and this is another. This is the goal of K-means. So all we want to do is that we want to find some K number of centers such that the data points that are in the same cluster are close as possible. And the ones that belong to different clusters, the distance could be large. Okay, so that's the main goal of K-means. And then now, and we can think about it mathematically now based on this explanation. First, we say that I should delete. I don't know if I should use this. Okay. Okay, so mathematically, we can think about it that here we have some parameters of K-means, and our parameters here are the means. So if you remember, we want to find some particular centers or centroids such that the distance between each data point in that cluster are as small as possible. So our parameters that we actually want to find here are the means. So for K here refers to the number of centers. So for K equal to 3, we want to find 3 different centers such that the distance between this center and then the data point in it is as small as possible. And this basically is just the Euclidean distance. Okay, so our idea or main goal is that we want to find our hypothesis function is that for each mean and then a data point, what is the distance between them? This should be small. And then the idea is for us to minimize this center or minimize with respect to mean. And this mean would now ensure this minimization of data points and each of the centers. So this is the hypothesis function for our K-means. And then with this hypothesis function, we can find a loss function. So given this particular function, we can find a loss function such that we know that with this particular hypothesis function, the difference between that and then what our data point is, it's going to be small. So we want to minimize this loss function. So then we have the optimization problem as largely having this hypothesis function, which we define as the mean of the cluster and then a data point minus the mean of the data point. And we are minimizing this with respect to mu. So largely it's still the same explanation that I gave earlier about having different centers. And then for each center, we want to find the distance of a data point to the center and make sure that this distance is as small as possible. And now with a loss function, what we do is that we have our model or our hypothesis function. And given this hypothesis function, we want to evaluate to see if this is the good function that represents our data in that case. So all we want to always do, or in machine learning mostly, is either we are minimizing this loss function. And so our loss function is just giving us the hypothesis minus x. And x here is the data point. So first, I explained that k-means, the main goal of k-means is that what we want to do is we are given a data set. And with this data set, we want to find k different centers. So when we say k, it just means how many centers that you want to have. So when we say k could represent any integer. It could be 3, it could be 4, it could be 5. So depending on the value of k. So in this case, in this example, let's say k is 3. So you're going to have a center. You're going to just choose a center here, like 3 different centers, another center here, and another center there. And the idea is that you want to calculate that the distance from this data point to this, it's small, because this is much closer to this center here. I don't know if you can see my weird annotations. Let me see if we can use a different color. Okay, let's see if yellow would work too. No, bad color. Red. Yep. So largely what we want to do is that we want to find a center such that the data point, so if a center is here and another center is there and another center is here, which I said k basically means the number of centers or centroids, okay? And here there are 3. So the idea is that we want to find these 3 different centers such that the distance from this data point here and then to this center, the center is just a point, okay? So the distance from this data point to this center is small. So you want to minimize this distance. And then if you look at the distance from this one to this data point, because this is a different cluster, and this is also like it's supposed to be in a different cluster. So we expect that the difference from the distance from this data point to this center should be maximized or large, I should say. And then this distance we want to have to be minimized. So we just expect that for each data point that is in a cluster, the distance with the mean is small. And this mean we have to find them. We don't know them. So I was just trying to look at this in how we would represent this mathematically. And to represent this mathematically, what we are looking, or what we try to do, is that we first of all need to define what our parameters are, right? So in our case, the parameters the parameters we're trying to optimize for are the means. So we know that it's the means that would help us be able to know that, okay, this should be one cluster and this should be another cluster, because the mean just describes the center. So in each data point that is in that particular cluster, the distance between it and its center is small. So they have one cluster and another cluster. So to help us do this, we need to find a function. So what we would end up learning actually is this hypothesis function. We're going to learn this hypothesis function, because now with this hypothesis function, we want to find the center that is closest to a point. So this again is our mean and this is our data point. So we find the distance between these two. And then what we are doing is that we want to minimize this with respect to mu. So we are choosing the mu that will give us that smallest value. But then if even we find this h theta, how do we evaluate that this h theta is good? Well, how do we check? And to check that, we just look at this hypothesis function that we would find and then subtract this from our data points. Okay, and this we define as our loss function. Our loss function takes our function. So I think maybe in unsupervised learning, maybe you defined it as f of x. So you have an f of x and then you have your input input x. Now in in ML, what we normally would do is now to minimize this our loss function. So if we're able to minimize this loss function, like get this loss to be as small as possible, then we'll be sure that our hypothesis is the right hypothesis that we have. So to help us, the optimization problem then is defined as this h theta of xi minus xi. So this is how we define a hypothesis function, and we want to minimize this with respect to mu. So this is the main goal. This is our goal. And then we now have to elaborate what do we mean by h theta. Okay, this h theta is defined as mu minus x, and then we have xi. Xi is just the data point in that case. Please, does this make sense? You need to really understand how this works before we move on. Samuel, you have your hand up, yes.
Okay, please, given a known data set now with this formula.
What?
Like, given a known data set, a known
data set.
A known one, like a data set that we have, like a
known data set. Okay.
Yeah, given a known data set, how do we compute this now? You get it? Like, how do we compute this hypothesis, first of all? You get it? Because right now I'm just seeing a theoretical formula, which I don't know how to apply given data set. So how do we apply?
Good question. And I have a very simple example to help us understand that. But first of all, I just wanted to make sure that mathematically this even makes sense to you before we move on to look at a worked example on that. So the main goal, I don't know if you get the main or high level idea of what the K-means is trying to do. Does that one make sense to you?
Yeah, I understand that. First of all, you're trying to look for the hypothesis function. You get it? And after that, after you get the hypothesis function, you use it to get the loss function. After that, you optimize, which is you're minimizing the center. You're like in the clustering, you have 3 clusters, and you're now like in one cluster, you're trying to minimize the distance between one data point to the other, just like the one you're pointing now. The blue one, you're now trying to calculate the distance from one to minimize the distance from one data point to the other, which is what you're trying to do, the optimization. Because why the loss function? You are trying to maximize the distance between one cluster. Yeah, you're trying to maximize the distance between one cluster to the other, cluster 1 to cluster 2. Am I right?
No, so the main goal is we want to minimize the distance from each data point to its centroid.
Yeah, which is what you're trying to do with the optimization.
Yes, exactly. Yeah. Good. Yeah, thanks. Yeah, exactly. That's what we want to do. So for the main goal is that for each data point here, we want to find the distance from that data point to the center, and also the same from this data point to its center. We want to make this as small as possible. So I like the question you asked about, okay, so how do you even do this, right? So to do this, what I gave here is a simple example. So here I gave some data points. So with these data points, we have x1 is defined as 2 and 0, x2, 1 and 3, x3, 1 and 4, x4, 1 and 1, x5, 2 and 3, x6, 0 and 5. This is being done by hand. So this is just like a simple thing to illustrate how it even works, right? So given this, we want to compute 2 full iterations. So I'll come to this Lloyd algorithm, but then first of all, we want to compute this. And first we have to initialize some clusters. So we need to define our K, okay? I'll come to how we define K, but first of all, we need to define K. And to define K, in this example, we give you a random initialization that the first mu, which is the first K, is defined as 1 and 3. I told you that it's a data point, okay? So if you take a Cartesian plane, for example, 1 and 3, you have the X here, this is 1, and let's say this is 3. So the center is here. You can think about it that way. And then we can also, of course, plot all of these ones. Okay, and then we have mu2, and mu2 is defined as 2 and 3. So we have 2 here, and then we have 3 here. Okay, now we have been given mu1 and mu2, which I'm saying that this mu's, you can think about them as your K. So this is K1 and K2. So here, the K here is equal to 2. And then we have given you the definition of the Euclidean distance. So the Euclidean distance is defined as a1 minus b1 squared plus a2 minus b2 squared, all square root. So now we want to know that if we pick this data point, and let's say it belongs to mu1, we want to make sure that the distance, if it truly belongs to mu1, then the distance between this data point and mu1 should be small as possible. And if it doesn't belong to this mu2, of course, that would have the larger distance. So how do we do that? We are going to do this through some iteration. So we already have our initialized k values. So we have mu1 is giving us 1 and 3, and we have the distance function. So we are going to calculate the distance of x1, that's 2 and 0, to what is the distance between that point and then mu1. And then we would calculate equally what is the distance between x1 and then what, mu2. And that's what we do here for the first round. So for the first one, we have distance from x1. So, and we are given the Euclidean distance, which is a1 minus b1 squared plus a2 minus b2 squared. So we're going to take 2, which is the first point here, the x value here, 2 minus 1, which is the mu of k1, plus 0 minus 3, which is this value. So 0 minus 3. And then this will give us square root of 10. Then we do the same for K2. For K2, we take again 2 minus 2, then 0 minus 3, and this gives us 3. So now we look at the distance of x1 to mu1, K1, and x1 to K2, which is the mu2. Which of these have the smallest value?
On the distance x1, I used to see 2 minus 1, I don't, and 0 minus 3, but for, you only compute the first two.
Am I still sharing my screen?
Yeah, sorry.
Yeah, your question, please.
Yeah, I because I can see that we have x1, x2, x3, x4, x5, x6, and also the value in brackets. And then when here it seems that you take x1 and x2.
Which one here?
Yeah, x1, 2.
Okay. I see your confusion. Okay, so let me just explain again. So first, we are given this data points, and then we give this random initialization. So these are not like, this could be any value, right? We give this random initialization. So we say mu1 is defined as 1 and 3, mu2 is defined as 2 and 3. So our first thing we want to do is that if we pick each data point, we want to calculate the distance from data point 1 to mu1, and calculate the distance from data points 1 again to mu2. And so how do we calculate the distance? We are calculating using this distance, Euclidean distance formula. And what this distance formula says is that we should take a1 minus b1. So you can think about it as x1 minus the x1 of x2. Okay, so we have, let me just write it here. So first, let me take x1. x1 is equal to 2 and 0. Okay, then we know that mu1 is defined as 1 and 3. Now, if we want to find the distance between what, x1, comma, I'll call this just what, mu1. This is defined by this formula, which is given to us as what, the square root of what, a1. In our case, this is 2. Okay, so it's gonna be what, 2 minus b1. In our case, we are finding the distance from x1 and mu1. So mu1, its x value is 1. So we're going to say 1 minus 1, all in brackets because this is squared. So we're going to say squared plus, then we take the next value. This is 0. So we're going to have 0 minus, we're going to subtract this from the y value of mu1, which is giving us 3. So we're going to have 3. And then we simplify this, okay? So 2 minus 1 is 1, so it's like 1 squared, plus 0 minus 3 is what? Negative 3. And this is squared, sorry. and this is squared. And this is going to simplify to, this is 1 squared is 1, minus 3 squared is what? 9. So we're going to now have square root of what? 10. And that's what we have here. And this is only the distance from x1 and mean 1. And we need to do the same for mean of x1, comma, mean 2. Okay, mean 2. And using the same ideology where we know that x1 is given as 2 and 0, we're going to have square root of 2 minus, now instead of what? Instead of mean 1 value, we're using mean 2. That's what we want to find. The first value here is 2. So we have 2 all squared plus the next value here in x1 is 0. So we have 0 minus what? Minus 3 in this case. So we have 3. And this is also squared. And 2 minus 2 is 0. So 0 squared, we still have 0 plus 0 minus 3. This is minus 3. Then we have 9. Then if we take the square root of this, it's the same as taking the square root of 9, which is equal to 3 in this case. So we got 3 here. So now we have calculated the distance of x1 to mean 1, x1 to mean 2. And given what values we get for the distance, we choose which of them has the minimum. And in this case, we see that this value, that's mean 2, has the minimum. So we are going to assign x1 to belong to mean 2. So that's what we do with the first. So we first of all have the data points. And for each data point, we were given some random initialization of the means. So what we want to do is to find the distance of each data point, and then the two different centroids, which I said are just the k values. And then based on which one is the smallest, we would then assign that we assign the data point to that particular cluster. Samuel, you have your hand up. You actually see 2 hands. Yeah.
Okay. You have calculated x1. You have calculated x1. How will you calculate x2?
In a similar way, x2 is given as 1 and 3. Okay. Yeah. So again, we are going to have x2 is given as 1 and 3. We are going to do it the same way. We know that we want to find the distance between x2. I don't know if I should. I think it's possible I can connect this and rather use that I hit with the writing. So it's the same thing that we are doing. We just have to calculate the distance like we did before. Okay. Yeah. So in the event for x2, it's a similar way we're going to do it. So first we're going to have x2. We know x2 is defined as 1, 3. Okay. So we're going to find the distance of what? x2 again, minus the same mean 1. So mean 1. And this is equal to, again, we're going to use the distance formula. And here it's 1 minus 1 all squared plus 3 minus 3 all squared. And this is going to give us 0. And then we're going to find again the distance of x2, comma, mean 2, okay? And this largely is equal to the same of square root. Now x2, again, we know it's 1 minus, that's this one, minus x2 here is 2, all squared, plus, now we have 3 minus 3 all squared. And this is going to give us 1. And that's what we have here. This is 1 and this is 0. Okay, so it's the same thing you're going to do. So question, is x2 closer to cluster center? Okay, yeah. So with this distance, if you look, this is 0 and this is 1. Do you think that X2 is closer to center 1 or center 2? Which of them? Looking at this distance, here it's 0 and this is 1. Which of them do you think is closer to center 1? Yes, because the distance there is smaller. Exactly. So yeah, so that's, I just had to do X1, X2. So X3, you do the same thing. X4, you do the same thing. So largely that's how this works. Okay. So if this makes sense, maybe we would just want to see how this propagates. So I just did for the first iteration and I put the results here.
I have a question.
Yes, please. Go ahead.
Is just talking about general optimization algorithms, is there a particular importance of starting with a kind of right value for your initial clusters? Or can you just pick a random number?
I mean, it results in the similar issues when you I mean, with every optimization problem, sometimes there's some, let's say if you start with 0, 0, you could probably go into some local optima and things. So
yeah,
you probably would not want to start with 0, 0 per se. So I would say, I mean, the random values itself, you could end up initializing, and these actually are the right centers that you get, and that's good. But otherwise, you would always still converge with k-means. So even if you start with random clusters, you would always converge because of this several iteration and recalculating at every point. So the good thing with k-means is that you would always converge. And
okay.
But just be careful. I wouldn't recommend that you initialize with 0, 0, for example, but any other value, yeah.
Okay. So are you saying it will take a longer time for you to be able to converge to the right kind of cluster?
Time convergence
value.
Time convergence wise, I don't think, I think k-means algorithm is, because calculating this distance is not a very complicated distance to calculate for. So I'm not very sure about the full time convergence, but I don't think the time convergence in itself should be take too much time. It's a fast algorithm itself. So
okay. So lastly, are you saying it's like best practice for you to like pick one of the data points as like the initial cluster data points?
Mm-hmm. I mean, you could try that. You could try using the data, like one of the data points as initial cluster, and continue to iterate to get the right one. So yes, that's good work.
All right, thank you.
Welcome. Okay, so yeah, so here I just had to show, so x1, x2, we do the same calculation. So we have the calculation for mu1 and each of the data points, and the calculation for mu2 and each of the data points. So maybe what I would recommend as a homework for you would be later, we just did this for x1 and x2. You could try to do this for x3 and x4 to see if you're able to use this formula and calculate the distances. And then the cluster assignments here for the first iteration is that based on these distances, x2 here, we calculated x2, this was 0, and then this was 1. We know that this belongs to what? Cluster 1. So that's why x2 is here. And we did for x1, we saw that 2 and 0, this was square root of 10, and then this was 3. And we know that this certainly belongs to the smallest distance is cluster 2. So we had cluster 2 in here for x1. So I just wrote what are the clusters for each of them. And then once you do this, the next thing you want to now do again is to update your centroid. So these were random values. Now, once you have gotten that, okay, these values are closer to this cluster 2, also these data points are closer to this mean. In here, we want to recalculate the centroid. Sorry, we need to recalculate the centroid. And to recalculate the centroid, all we do is to take the data points that are in that cluster. So here we have 1 and 3, 1 and 4, 1, like each of the data points. So this is just the X and this is the Y values. Then we find the mean. So if you take the X, if you take X2, X3, X4, and X6, then we just want to find the mean of this. So to find the mean, you take all the X values. So these are only the X values and these are the Y values, and there are 4 different values. So to find the mean is just adding all of it over 4. And then this gives us the new centroid as 3 over 4 and 13 over 4. We do the same for mu2. Mu2 now has values x1 and x5. So x1 is 2, 0. So we have 2 here. And then x5, it's 2. So we have 2 plus 2 divided by 2, comma. Now for the other value, we have x1 is 0 for y, and then we have 3. So that's 0 plus 3, all divided by 2. And that gives us the new centroid for that, which is 2, 3 over 2. So now with these new centroids, we would do the same thing again. Now we calculate the distance of x1 with this mu and x1 with this mu. Then we see which of them is the closer. I think with 2 iterations, you should converge. So to know whether you should keep doing the iteration, what happens is that once these mu's that you have gotten, they don't change again, then you know that you have gotten to the conversion. Like these, the actual mu's have converged. So that's how this works. Does this make sense, please? So the homework here I'll give to you is to try to see if you can complete these distances, and then also do for the second iteration. So now you have the updated centroid. So use these updated centroids and recalculate the distances and see which clusters would belong to which clusters in that way. It's just a good exercise to do. But this like how the idea of k-means work. Yeah, so the algorithm for k-means, here we would just start by initializing centers. And with the centers, what we do is now to calculate the sample that is closest to the particular center. So that's what we saw. And then we recompute the mean, which is what I just showed to you, how to calculate the mean again for each of them based on the classes they've been assigned to. And then if we do this, then we go back again and then recalculate this. We keep doing this again and again until we don't observe any change. Then we would now return this optimal mu 1 to mu k. So depending on how many clusters you have. So largely this is how the k-means algorithm works. I think for your lab today, you would see how to do this. So I just got a beautiful GIF on how this works in action. So we see it started at the center, and then the centers keep changing because you keep updating the centers by calculating the distances to see how far each data point is to a center, and then you re-update the centroid. So you notice that the centroids would keep changing and changing. So this started with 69, went to 89, 87. So you just keep seeing the centroids. These are the centroids. They are changing as you keep going through the algorithm. Okay. So the question probably someone will be asking would be, so I said initialize cluster, and then I just said, okay, as it's k equals to 2, how do you actually know which cluster, how the value of k you should select? The good news is that there are several ways in which you can select k. One of the methods is what we call the elbow method. With the elbow method, what happens is that we want to run several values of k and then calculate what we call the within cluster sum of squares. And then we want to choose the value where the sum of squares is diminishing. So on this y-axis, we have the sum of squares, and then we have the different values of k. So we're going to start with k equal to 1, and then we run all the iteration and then see what the sum of square is. Then we set k equal to 2, we see what the sum of square is. K equal to 3, we see what the sum of square is. And then with the elbow method, we are going to choose the value where the sum of squares is the smallest. So you can think about it as your elbow. So this point, this is where the elbow is. That's where the sum of squares is as small as possible. And now what do I mean by the within cluster sum of squares? So within cluster sum of squares is giving us the distance of each data point and its cluster. And then we do this across the sum of all the clusters. So you pick for each cluster, you calculate the distance from each data point to the cluster, and then you sum this up. Then afterwards, so that's it for this first sum. And then for the second sum, we are doing this over all the other clusters, all the clusters that we have. And then we get the value for the within cluster sum of squares. So this just shows us a plot of that. And then the elbow method, where it is the sum of squares, the lowest, the smallest is where we choose k to be 3. So for this example, k equal to 3 is the best. Then we look at another method, which we call the Slowett method. With the Slowett method, it's giving us with this formula. So what we do with Slowett is that we want to calculate BI minus AI all over the maximum of AI and BI. But what are these values? So AI is largely the average distance of a data, the center and all other data points that are within the cluster. So if you pick cluster 1, what are the average distance between each data point and then that cluster? And then BI gives us the distance of the data point and all other neighboring clusters, so the ones that are out of the cluster. And we want this value in itself to be large. This value should be large, but we want this value to be very small. And so with the Slowett score, we do it the same way, also like we saw with the elbow method. We are going to do this for different values of k. We calculate the Slowett score. Just that with the Slowett score, we want the value to be the value should be between +1 and -1 with this formula. The value will always be between +1 and -1. However, a high value is usually desirable. So the higher the value of the Slowett score, the better that you have done the correct clustering. So that's the main difference between this and then the elbow. Elbow, we use the within cluster sum of square, and so we look at the minimum. But if you're looking at the Slowett, you have to think about finding rather the highest value, the maximum value, and it's usually between +1 and -1 with the Slowett method. So yes, based on this, I have another quiz, but I want to first of all ask if everything is clear for everyone so far. So far, so good. So we look at which of these two data sets you think k-means will struggle to cluster. So we have this data set 1 and data set 2. So you can just write either 1 or 2. Which of them do you think that k-means will struggle to cluster based on your understanding of how k-means work? Which of these do you think k-means would struggle to cluster? Would k-means be able to cluster both of them? Would it be able to cluster only 1 or 2? Or it will not be able to cluster any of them? 1. You think it will struggle to cluster 1? Okay. All right. Could someone just unmute and tell me why they think it's going to struggle to cluster 1?
That's because the blue is more spread. The blue in the data set 1 is more spread than if you look at data set 2, the clusters are more together than in data set 1.
Okay. But why has the spread got to matter with why k-means will struggle to cluster?
The center of the blue is how do I put it? The center is too far from the data point.
Okay. Yeah. So the center, the data point, you think the center will be here, and if the center is here, it will struggle to cluster this?
Yes, I think so.
Okay. All right. Thanks. Any other person?
Let me give it a try.
Yes.
Okay, for data set 1, the data are not like, the shape is not round. And if the algorithm wants to cluster, it clusters the data point according to the distance from the center. The data point at the edges of this blue may be classified as green because the centers will be like more or equal to the distance from the center of this blue to the green data also.
Yeah, true. Yeah, so yes, so this it's the one that k-means will struggle to cluster. And normally one thing about k-means, like you explained, that it's assumes that the clusters are like spherical. And if we have some overlap or non-spherical shapes, then we see that k-means will actually struggle to cluster the data set. But these ones have like these spherical shapes. And so the mean to be here, you can easily find the distance of each of them to the mean of that cluster easily. But with this, it's maybe hard to achieve that. So yes, you were right with the answer. And so this brings us to the problems of k-means in particular. So I think one of the problems we've just seen is that it creates like spherical shapes. And so if you do not have the spherical shapes, it's probably will end up putting the center of each of some of the data sets. The center would, it will end up wrongly clustering some of the data sets to some other clusters when they don't have the really real spherical shapes. And another problem with k-means is that it does what we call hard clustering, in the sense that we notice that when it's assigning one data point to a cluster, there's no particular certainty that I'm assigning it to this data point because I have this 70% high probability that it should belong to that data set. We do not do that in k-means. We just assign it to a cluster. So it does hard clustering, which sometimes doesn't help when there is uncertainty in that sense. All right, so I introduced this Gaussian mixture model pretty much quickly because I wanted us to, we just understood there are some problems with k-means. It does this hard clustering. And the good news with Gaussian mixture model is that that is like now a probabilistic model. It's also for clustering again, but it's a probabilistic model. And usually with Gaussian mixture model, we assume that the data in itself is modeled by different or several Gaussians. And we identify each Gaussian with a k. So for Gaussian 1, that's k equal to 1. It just tells us, it just describes the data as the cluster as a Gaussian, and k equal to 2, the second cluster, it describes it as another Gaussian. So for each k, you have a mean, you have a covariance, and then you have a mixing coefficient. So think about it that these are the data points that we have. So for each data point here, we have one cluster, one Gaussian, and then we have one Gaussian. And then for each Gaussian, you have the mean, and then you have here's the standard deviation, but then we are dealing with several Gaussians, so we rather describe this using the covariance. And each cluster is a Gaussian. So I just added the formula of the Gaussian distribution. I know for the last week or two, Tejumade hit a lot on this different mixtures and stuff. You did a bit of ML, maximum likelihood estimations, which you looked at Gaussian Gaussian distributions and stuff. So for each cluster, we have a Gaussian distribution. For each cluster, we have another. And this mixing coefficient helps us tell, if you pick a data point, what is the probability that it comes from this cluster or that cluster or that cluster. But remember that instead of looking at these data points as they are, we look at them as different Gaussian distributions in that sense. And with Gaussian mixture model, what we try to do is that we want to find the probability. If you pick a data point parameterized by the value theta, it's giving us the summation of k equal to 1, that's the clusters, to k, defined by our mixing coefficient, and then the PDE of that particular distribution. So here we define our theta as a list of values, which we have to find. Remember, in k-means, the theta here was just the mean that we needed to find. In Gaussian mixture model, our theta is made up of a set of values, and the set of values are what we describe here first: the mean, the covariance, and then the mixing coefficient. So we need to be able to find these values. These are the parameters of our model. These are the parameters of our model in Gaussian mixture model. And this is a set of parameters that we would have to find to describe this, okay? And to do that, we need to find values that would help us maximize the likelihood of this data. And how are we going to do that? There is, just like in k-means, we have the Lloyd's algorithm, which we saw earlier. I showed to you after we did the calculation, I showed you the Lloyd's algorithm. In Gaussian mixture model, we rather have the expectation-maximization algorithm, which would help us actually find the values of this theta. And how does this algorithm work? It works in 2 different steps. We have the E step and then the M step. the E step, what it does is that it helps us estimate the probability that each data point was generated by each of the Gaussian. So for each, if you take a data point, it calculates what is the probability that it was generated by Gaussian 1. So like if I pick a data point, I want to know what is the probability that this was generated by cluster 1, or it was generated by cluster 2, or it was generated by cluster 3. So I need to find these values, right? So in the first step of the expectation maximization algorithm, what we do is to find that each data point was generated by each of the Gaussian. And how do we do that? We do that by calculating the responsibility. So if you pick a data point, we calculate the responsibility by taking the mixing coefficient and then the PDE and summing this, dividing this over all the clusters that we have, the probability of these other clusters that doesn't belong to this. And then we have the first step we should remember with the E step is that we have different Gaussians, and for these Gaussians, we need to calculate the E step, or we find the E step, which helps us find the responsibility of each data point to each cluster. So it will tell us that, okay, for cluster 1, the probability that data point is from this cluster 1 is, let's say, 0.2, and the probability that is from cluster 2 is 0.3. And then the probability that is from the other cluster is, let's say, 0.6, because this should add up to be 1, okay? So then we have the M step, which then updates the means and variance of the distribution. So we already have 3 parameters. We have the mean, we have the covariance, and then we have the mixing coefficient. So the first step will just tell us the responsibility of each data point to that. And the end step now helps us to update the values. So it's the same iterative process like we saw in K-means, just that this time around, we are calculating probabilities that it belongs to this cluster or that cluster. Instead of like K-means, we just do a hard clustering, just find the distance and put it there. Here we calculate a probability that it comes from a particular Gaussian. And in the M step, what we do is that we want to find the updates of each of them. And to find the update, again, we have 3 different parameters we are calculating for. We want to find the mean, we want to find the covariance, and then we want to find the mixing coefficient. And to find the mean, we are going to use the responsibility of each data point again. So the values we got from the E step, which tells us the responsibility of each data point coming from a particular Gaussian, we are going to use that to re-update the mean of it. And to update the mean, we're going to find the summation of the responsibility, which is defined as NK, and then the responsibility of this XN, given that it comes from this particular Gaussian. So we do that to update our mean K. So for each of the Gaussians, again, we're going to calculate what its updated means are. So if we pick 3 different Gaussians, we are going to have 3 different means. And for this E step, we take a data point, we find what is the probability that is coming from a particular, the Gaussian 1, which is K equal to 1, or Gaussian 2, which is K equal to 2, or Gaussian 3, which is K equals to 3. Now, once we have the responsibility, we want to now re-update what the initial means were. And to update the means, we're going to just take the responsibility that we already calculated for, right? The summation of all the data points and then the responsibility of each. And then we sum this over. So this already is like we're finding the responsibility 1/8, that's the mean. And then over all the responsibility of each of them. So it's the formula of calculating for mean, basically. So with mean, you add all of the points and divide by the total number. So that's what we're going to do here. Then with the covariance, again, we would use the NK. So this is similar to the covariance formula. What is the covariance formula? Here we have the matrix because we are multiplying by a vector. So we have xn minus mu k, xn minus mu k transpose. And again, we use the responsibility. And then we now have to find our coefficient mixing parameter, which is now nk divided by n. And nk, we know that nk is defined as the summation of all the responsibility that we got from the E step. So largely, the M step will always use the values that you got from the E step and then reiterate the process. And here we measure the log likelihood. So what is the log, like the probability that this data is actually from this Gaussian? That's what we do with Gaussian mixture model. So we are going to continue this process, an iterative process. You do the E step and the M step, the E step and the M step over and over again till your log likelihood stops to increase at a point. Then you know that you have gotten to the right clustering for your technique. So I put another expectation maximization algorithm. So here we have several iterations. As the iterations are increasing, we see that the log likelihood of the data keeps increasing over time till you get to the point over there. And then you notice that after this number of iterations, the log likelihood becomes stabilized, and then you can end your iterations there. So the high level idea, or why I added this the GMM, was to let you see that with k-means, we do a hard clustering. With Gaussian mixture model, we do a soft clustering by calculating probabilities. And to calculate the probabilities, or help us do it, we use the expectation maximization algorithm. And it's composed of 2 steps, the E step and the M step. The E steps just gives us the responsibility that each data point comes from a particular cluster. And then the M step now helps us re-update our parameters. And the parameters we want to optimize for are 3, the mean, the covariance, and the mixing coefficient. And then we get to know that once the log likelihood increases and gets to a point that's here, then we can know that at this point, we can end our clustering. We have the right clustering.
Does this mean that the GMM model is more accurate than the K clustering?
Yes, most likely the GMMs, because it uses the probability, it's able to tell with either a high probability that it comes from a particular cluster, right? Because of the soft clustering approach. And so you can look that it's able to really cluster different types of shapes or different types of shapes of data sets, right? With the Gaussian mixture model, unlike k-means, the way it works. So you can think about it that it probably will provide more accurate clustering over k-means, yes. Okay, so let's do a short quiz. Quiz 4. So I asked indicate true or false. So again, we use the charts. Okay, and then something I should mention with the this Gaussian mixture models probably is that so you need to start also with initializations before you now find the responsibility of each of the data points to it. Okay, thanks, Tejumade. So you can find what you can do is that you could use k-means first and find the initialized values like the mean, the covariance, and then the mixing coefficients. And then you start from there to now use the E and M step. So I think that's why Tejumade added in the chat that it's a special case of GMM. So you could use k-means first and then continue with the GMM algorithm, and then you can update the process. So just something to mention. Oops, I've displayed the answer. I'm sorry. Okay. Anyway, I still ask, indicate true or false to the following statements. The first statement is that GMM uses hard classification, while k-means predicts probabilities. True or false? True or false? False, okay. Yes, it's GMM using soft classification, and k-means rather uses hard classification. Good. And 2, GMM assumes that the data is generated by a single Gaussian. True or false? Okay, false. False, yes. So we saw that it assumes that the data is generated by different Gaussians. So for each cluster, we have one Gaussian. For each cluster, we have another Gaussian, right? Okay, and then the pop quiz 5 is, what does the E step in the EM algorithm for GMM achieve? The E step. So A is that it updates the values of theta to maximize the likelihood of the data. And B, it computes the probability that each data point belongs to each of the Gaussian distributions. And then C, it predicts hard classification for each of the data points. And then D, it finalizes the values of theta after reaching the local maximum of the likelihood function. Okay, I'm seeing B. Yep, B. Okay, it's confused the probability that each data point belongs to the Gaussian of the distribution. By doing what? By finding the responsibility, right? So the formula that we saw, what it does is to find the responsibility of each data point to a particular or to each of the Gaussians. Yeah. We were supposed to take another 5 minutes break, but given that we are running out of time, I think we'll probably just continue with the last part of it, which is PCA. So just a recap so far, we said we had 3 different types of unsupervised learning techniques. We said clustering, dimensionality reduction, and association, and we're focused on clustering and dimensionality reduction. And the clustering, we saw k-means as hard clustering. We saw GMM as soft clustering. And then with dimensionality reduction, we're looking at PCA. So what is PCA? PCA is just a type of dimensionality reduction technique. And the idea is that if you're given this, let's say you take this data in a high dimensional space, we want to be able to project this to like a lower dimensional space, which we'll be able to work with easily. But why do we have to do that? With PCA, it's largely difficult to train, and not PCA is difficult to train, but like working with large dimensional data is difficult to train. And usually because of the difficulty in training, it's from the computational power and time you spend in it. And also it tends to be hard to visualize high dimensional data. And so that's why doing PCA, it's pretty much a good thing to do when you're working with really high dimensional data. So first we have different, if you have to do PCA, there are several steps involved in carrying out PCA. So there are like 6 major steps. The first step is to standardize the data. The second step is to calculate the covariance matrix. The third step is to calculate the eigenvalues and eigenvectors of the covariance matrix. And the fourth step is to sort eigenvalues and their corresponding eigenvectors. And then you choose what your k eigenvalues are and form a matrix of eigenvectors. And then you can now use this to project the data, or you use to transform the data so that you can project it to a lower dimensional space. But what I'm going to do is that for all of these steps, we're going to just walk through them simply with an example. So the first thing is we have a data set. And with this data set, the first thing we said is we want to standardize the data. And to standardize the data, we can use any standardization formula. There are several standardization techniques. So we are using this, which we find x minus mu all over the standard deviation. Then the mu, we calculate for the mu for each of the data set, each of the features of the data. So F1, we find the mu, which is 1 plus 5 plus 1 plus 5 plus 8 divided by 5. We get 4. Then you do that for F2, you get the mu as 3, F3, the mu as 3, F4, the mu as 3.4. Then we find sigma, which we find, again, with sigma, what you do is that you find the mu, and then you subtract this minus each data point from the mu all over 1 over n. And then this gives us 3, this gives us 1.58. So we get the values of all of the sigma. Then what do we do? To standardize this data, we're going to apply this to this data. So what do? We want to take x minus the mu all over sigma. So you take 1, that's x, minus mu. The mu here is 4, and divided by the sigma, which is 3, you get minus 1. And so you do that for all of this data sets, and then you have the standardized data set. And with this standardized data set, we see how it is now. So you put the values to be between certain ranges. So that's what we do with the standardization. And like I said, you could use some other different formulas for doing the standardization. Our next step is that we want to calculate the covariance matrix for the features in the data set. And to calculate for the covariance matrix, you can think about the covariance matrix as this. So we have in the main diagonal, we have the variants, and then we now have the different, the covariance for F1 and F2. So each of the 2 features, with covariance, we are measuring the relationship between 2 random values. So for F1, for example, we have covariance of F2, F1. covariance of F3, F1. And I provided the formula for this covariance matrix here. So to find F1, what we do is that we take our data point, which in this case, we had this as -1, okay? So we take -1 and subtract this by the mean, square it, and then do that for the next values, for all the values, for all of these values. So we take this one, subtract from its mean, and then we square it, do that for this, do that for -1 and this, and then we add everything. So here we get the variance to be 0.8. We get the variance to be 0.8, and then we have the covariance metrics now. So we first standardize the data, use the standardized data, and then find the covariance metrics of the standardized data. So to find the covariance of the standardized data, we get this matrix here. So it's an entire matrix. So we find the covariance metrics, okay? Then once we have this covariance matrix, we are going to work with this covariance matrix now. And with the covariance matrix, we can define this as our square matrix A in our case. And then we want to find the eigenvalues and eigenvectors of the covariance matrix. And largely, we want to find AV, which is equal to lambda V. So largely, you can think of eigenvectors is that eigenvalues scale proportional to their eigenvector. So as the eigenvectors increases, you have a higher value of the eigenvector, then the eigenvalue also scales proportional to how the eigenvectors scale. So that's why we have this AV is equal to lambda V. And the lambda here is the eigenvalues. And the V are the eigenvectors. We would first of all want to find the lambdas, which is the eigenvalues, and then we use this to find the eigenvectors. I know that in one of your classes, you did linear algebra, which I joined the class. I think you had a class on calculating eigenvalues and eigenvectors. Correct me if I'm wrong, Tejimade, but I think I do remember that. But it's the same technique that we use here. So now we have a covariance matrix, and with the covariance matrix, we want to find the eigenvalues and eigenvectors, right? So now, how do we do that? So we already know that, okay, if we take our metrics, is A minus lambda I. So I here is just the identity matrix, okay? So depending if it's in our covariance matrix, if it's a 3 by 3, the identity matrix is a 3 by 3. So we find the determinants of our matrix A, that's our covariance matrix, minus lambda I, that's the identity matrix, and equate this to 0. This would help us solve this equation easily. And now this is what we've done here. So this is the determinant of A. So this is A, this is 0.8 minus lambda. We're still using these values, this covariance matrix. You see 0.8 minus 0.25, 0.03 is the same thing we're using here. But this time around, we know that we take A and subtract lambda I, and I here, I told you, is the identity matrix. So we have this matrix here. Now we need to solve this equation, and to solve this, we want to set its determinants to 0. So if we set its determinants to 0, we can find these values of A, because now we have determinant of A minus lambda I equal to 0. We know I. Now this lambda would be the only thing we need to find. So we can easily solve this equation and find lambda. Solving this, it's the same if you have any metrics and you have the determinant. So like with a 2 by 2, I don't have so much time. If you have a 2 by 2, if I give you a 2 by 2 matrix, and let's say this is 2 minus lambda, this is 1, then this is 0, and let's say this is 3 minus lambda, you can find your determinants easily. And the determinant, you know that you multiply these two, so you have 2 minus lambda. This is just an example, but this matrix is much bigger. This minus lambda minus this times this, which is 0, and you don't need to have to set this to 0. So if you simplify this, you're gonna have 6 minus 2 lambda minus 3 lambda, now minus lambda squared, and this is 6 minus 5 lambda minus lambda squared equal to 0. Now you can solve this difference easily, right? So It's the same thing you have to do here. We need to set this, find the determinant, set it to 0, and then you can find the values of lambda. Now, once you have the values of lambda, what do we do? Because now the values of lambda, just as a reminder, these are our eigenvectors, okay? So now once we have our eigenvectors, we can use them to find our eigenvalues. We need to find our eigenvalues. So we need to solve, now we know lambda, and using the same equation now times this v equal to 0, we can solve for the vector eigenvectors. So if we pick the value of lambda, the first value of lambda, so wherever you see lambda, you put the value that you already got for it in, and then multiply this by your series of eigenvectors. So here it's v1, v2, v3, v4. Okay, so if you have this, you can't also solve this again because now you know lambda. And so you can easily solve this equation by using any matrix solver. So here you can use the Cramer's rule. There are other Jacobian and others. You can use any of them to solve for v1, v2, and v3. And then you're gonna get the values for your eigenvectors. So for lambda equal to 2.5, that's the eigenvalue, you have this corresponding eigenvectors. And I told you that if you scale this eigenvalue, then this eigenvector scales proportionally. So we're going to do that for all the lambdas. So if you pick eigenvalue, and then these lambdas, which are the eigenvalues, we just call them E1. So for eigenvalue 1, these are its eigenvectors. So we have them here. Eigenvalue 2, these are its eigenvectors. Eigenvalue 3, we have these eigenvectors. Eigenvalue 4, we have these eigenvectors. Now with this eigenvectors, which is now a matrix, we would have to now choose. So now in PCA, what happens is that the first eigenvalue contains the maximum, it maximizes or contains the maximum variance that we have. So if you have this data points here, you have these data points just as an example. The eigenvalue is going to tell us the direction that contains the maximum variance. Okay, so in this case, if you look at this data set, where we have the maximum variance will be along this direction. And so the eigenvalue 1 will give us this direction, that the values, the direction along where the maximum variance is. And the second eigenvalue is going to be the one to also tell us where this which direction has the second maximum variance. So in this case, you can think about it this direction. So this will be eigenvalue 2, and this is eigenvalue 1. So these eigenvalues just helps tell us how much information, maximum variance we can get from which direction. So if you have the data set, you want where you can have maximum variance so that you take that direction. And if you want only one eigenvalue, you think that with just that one eigenvalue, you are able to get the most useful information from your data. You can work with only that. And so we have eigenvalue 1, eigenvalue 2, and their corresponding eigenvectors. So now we decide, okay, whether we want to do choose 2 eigenvalues or 3. You have to decide that. And so we have, so now we have this. So if we select, we pick the top k. So k is still any, you could take k as 2 or 1. So if we pick k as 2, that's the top 2 eigenvalues. This will give us a 4x2 matrix. And then we want to now project this 4x2 matrix onto our data sets. And how do we do that? We're going to take our transform data set again, the data set that we found the covariance and we standardized it. We're going to take that, and then we're going to take that feature matrix and multiply by this top k matrix that we have. And then this will give us our transform data. So this is our data set. We multiply by this 4x2, and then we get a 5x2 matrix. So it was a 5x4. Now we have a 5x2 matrix. And then this, largely, you can work with only this. And this is just the top 2 principal components. So this is how we go through the steps of PCA. So we standardize the data. Once we standardize the data, we find the covariance of that data set. And with that covariance data set, we want to calculate the eigenvalues and eigenvectors of it. And then once we calculate for them, we then take the top k eigenvalues from it. So in this case, it could be 2. So we take 2, and with the 2, we now project this data set where we take 2 and multiply by our feature matrix that we earlier had, the one that we standardized. And then once we multiply it, we reduce this to from a 5x4 to a 5x2 matrix. And this now is the transform data that you can work with. And then maybe I should just mention, so I included a link. So for each of the slide, I included a link to the tutorial because I got this from a tutorial. So I included a link there. I think for any other thing that I used to, I put the reference there. So if you need like further information or anything, you could just utilize them. I would want to summarize for our class today. So today's class was unsupervised learning. And we learned that unsupervised learning is just learning from unlabeled data. And we understood that we have 3 major types of unsupervised learning techniques. And these are clustering, dimensionality reduction, and association. And we focused our attention on the first 2, that's clustering and dimensionality reduction. And then we focused on the clustering, which was k-means and GMMs as algorithms. And we understood that both are clustering approaches. And k-means, what it does is hard clustering. It just uses the Euclidean distance to calculate the distance from each data point to a centroid or a cluster, and then assigns the one that has the minimum distance. And then GMM, that's what we call the soft clustering, that uses a probabilistic model. And how it does this is using what I call the expectation-maximization algorithm, which is the E step and the M step. The E step just helps us calculate the responsibility of a data point belonging to each of the Gaussians. And based on this responsibility, we use the M step to update the parameters of the model. So we update the mean, we update the covariance, and then we update the mixing coefficient. And we finally looked at PCA also as a dimensionality reduction technique. And we understood that with PCA, there are some steps that you follow to do PCA. Largely, we standardize the data. Once we standardize the data, we find the covariance matrix of the standardized data. Then we calculate the eigenvalues and eigenvectors of the standardized data. And then we choose the top k, because the top k eigenvalues would be the ones that maximize the variance of the data set. And that's what the direction where the maximum variance is. And that's what we are looking for. So we would choose the top k, and then based on the top k, we then multiply this by our standardized data to get the reduced dimension of our data. So that's actually like the main or high level concept of what we covered today. Okay, and then I added the references that I used to prepare this. So if you want more lectures or you want to look at things into details, you can find them. The links are here. And also there are links in some of the slides where I made use of any material there. So yeah, thanks very much. That's very much about it.